Traditional power substations rely primarily on wired communication systems, often utilizing fiber optic cables for data transmission. While these systems are reliable, they tend to have longer latency and slower communication speeds. This can cause delays in transmitting critical data between substation components and control centers, which in turn affects the overall response time for decision-making and fault detection. In contrast, quantum technology-based substations leverage 5G wireless communication, which offers ultra-fast, low-latency communication. This enables near-instant data transmission, improving the real-time responsiveness of the substation. The high-speed communication is especially useful in scenarios where quick adjustments or emergency interventions are needed. Quantum mechanics introduces us to the wonders of the microscopic world. The concept of quantum was first proposed by German physicist Planck in 1900. He suggested that the energy involved in light radiation and matter interaction is not continuous but exists in discrete packets, called quanta. This discovery reshaped humanity's understanding of energy. In 1905, Einstein expanded this concept, explaining the photoelectric effect using quantum theory, which highlighted that light consists of particles, or quanta. This new understanding led to major technological advancements, including atomic energy, semiconductors, lasers, nuclear magnetic resonance, superconductivity, and global satellite positioning systems, which have fundamentally transformed human life. Quantum precision measurement is one such breakthrough. Accurate measurement is the foundation of scientific research and has driven technological advancements throughout history. Quantum precision measurement allows for highly sensitive measurements of time, frequency, acceleration, and electromagnetic fields, improving capabilities in areas such as medical treatment, deep-sea exploration, and detecting dark matter and energy. In power systems, quantum precision measurement can capture microchanges, such as early abnormal conditions in equipment, and transmit the information quickly to improve emergency response efficiency. For example, quantum current transformers at the Anhui substation use diamond as a sensing material to significantly enhance current measurement accuracy, achieving a nearly 100-fold improvement. China Anhui Hodian Quantum Demonstration Station has applied quantum computing in power grid simulations, such as load forecasting and stability analysis. By leveraging a 72-qubit superconducting quantum computer, they are exploring new ways to model energy flow distribution more accurately, optimizing market rules and pricing mechanisms. Quantum technology in power substations leverages quantum mechanics principles to enhance performance and security. Quantum sensors detect small changes in electric or magnetic fields, improving real-time monitoring of power quality and equipment status. Quantum cryptography, particularly quantum key distribution (QKD), offers unbreakable encryption, ensuring secure communication between substations and control centers. Quantum computing, though still developing, has the potential to optimize grid management and energy distribution. Meanwhile, 5G technology enables ultra-fast data transmission, real-time monitoring, and edge computing, which improve decision-making and automation in substations. This combination facilitates better integration of renewable energy, enhanced grid security, and the development of smart, decentralized power systems. However, challenges such as technical limitations, cost, infrastructure upgrades, and regulatory frameworks need to be addressed for full integration. Take few real examples. The State Grid Corporation of China (SGCC) is a global leader in applying quantum communication technology to improve the security of its power grid. By implementing quantum key distribution (QKD), SGCC ensures that encrypted data transmitted between substations and control centers is protected from cyberattacks. This pilot project, combined with the exploration of 5G, aims to create a highly secure and automated grid. The use of 5G provides low-latency communication, allowing real-time monitoring and control of substations, enhancing grid security and performance. In the European Union, the quantum flagship projects focus on integrating QKD and quantum sensors in power grids to secure communication and monitor equipment. Quantum sensors detect minute changes in electric and magnetic fields, improving fault detection and preventive maintenance. The projects also explore quantum computing for solving complex problems like load forecasting and grid optimization, while leveraging 5G networks for real-time data transfer and edge computing for localized decision-making at substations. Japan's NTT is also experimenting with quantum communication in collaboration with power utilities, focusing on using QKD to secure communication between substations and headquarters. NTT is integrating 5G networks to support faster data transmission and real-time decision-making, enhancing the efficiency and security of power grid operations. In Europe, several countries are implementing smart grid projects that use 5G and edge computing to modernize power substations. These initiatives focus on real-time automation, self-healing grid features, and the integration of renewable energy sources. 5G ensures reliable communication, while edge computing processes data locally to improve grid efficiency. These projects lay the groundwork for future integration of quantum technology to further enhance grid management, security, and resilience. Quantum technology and 5G-based power substations provide transformative benefits that elevate power grid operations to a new level of efficiency and security. The integration of quantum key distribution (QKD) ensures that data transmission is protected with unbreakable encryption, addressing the growing concerns over cybersecurity threats in critical infrastructure. Additionally, 5G's ultra-low latency and high bandwidth capabilities allow for real-time data processing, enabling substations to transmit vast amounts of sensor data instantaneously, thus improving responsiveness to grid anomalies and emergencies. This facilitates near-instant decision-making during grid faults or overloads, significantly reducing outage durations and enhancing overall grid stability. The deployment of edge computing within these substations further reduces the need for centralized control by allowing data to be processed locally. This results in semi-autonomous operations, enabling substations to manage tasks such as load balancing, fault detection, and power flow management independently. Moreover, quantum technology enhances the grid's ability to integrate distributed energy resources like solar and wind power, making the system more adaptive and capable of handling renewable energy fluctuations. This shift toward smart grid capabilities reduces reliance on fossil fuels, helping meet sustainability goals. The inclusion of quantum sensors takes monitoring and maintenance to the next level by detecting even the smallest changes in the electric and magnetic fields. This high precision allows for predictive maintenance, enabling issues to be identified and resolved before they cause major disruptions. This leads to improved grid reliability and fewer power outages. Additionally, quantum computing offers the potential for advanced analytics, allowing power systems to handle complex optimization problems more efficiently than traditional systems. This speeds up fault detection, improves energy distribution, and ultimately strengthens the overall stability and resilience of the power grid. Quantum technology and 5G-based substations represent a critical leap forward, offering improved cybersecurity, real-time communication, grid efficiency, renewable integration, and reliability, positioning them as essential infrastructure for the future of energy management. Security is another area where quantum-based substations have a significant advantage. Traditional substations use classical encryption protocols that are vulnerable to increasingly sophisticated cyberattacks. While encryption methods can provide some security, they can still be breached, leaving the system exposed to unauthorized access or data interception. Quantum-based substations, on the other hand, utilize quantum key distribution (QKD) for secure communication. With QKD, encryption keys cannot be intercepted or tampered with without detection, providing a near impenetrable defense against cyber threats. This level of security is critical as modern power grids become more interconnected and vulnerable to cyber attacks. Quantum technology-based substations, in conjunction with 5G, represent a new paradigm in power grid management that addresses many of the limitations inherent in traditional substations. One of the most compelling advantages is the shift from centralized to decentralized data processing. Traditional substations rely on central control systems to analyze and process data collected from various sensors and devices within the substation. This centralized approach introduces inefficiencies, as data must be transmitted over longer distances, often causing delays that affect the timeliness of critical decision-making. The time it takes to detect and respond to a grid fault or other operational issues can lead to increased downtime and potentially costly power outages. In contrast, quantum technology-based substations utilize edge computing, which processes data locally at the substation level. This means that data collected by sensors can be analyzed in real time, enabling faster decisions without relying on central systems. The introduction of quantum computing as it becomes more feasible further enhances this capability by solving complex optimization problems related to power flow, load balancing, and fault management. Quantum computing has the potential to process vast amounts of data more efficiently than classical computers, which is crucial for managing the complexity of modern power grids, especially as they integrate more distributed energy resources like solar panels, wind turbines, and energy storage systems. Another critical area of advancement in quantum-based substations is the use of quantum sensors. Traditional substations rely on conventional sensors, which are typically limited in their sensitivity and precision. These sensors can detect major changes in system conditions, such as large fluctuations in voltage or current, but they may fail to capture minor anomalies that could signal early signs of equipment degradation or malfunction. Quantum sensors, on the other hand, offer significantly enhanced sensitivity and precision. They can detect even the smallest changes in electric or magnetic fields, allowing for the early detection of potential problems before they lead to major system failures. This level of precision not only improves overall substation reliability but also enables predictive maintenance strategies. Rather than waiting for equipment to fail, quantum-based substations can anticipate problems and perform maintenance proactively, reducing downtime and extending the life of critical infrastructure. Security is another area where quantum technology-based substations provide significant benefits over traditional systems. As power grids become more interconnected and rely on digital communication for control and monitoring, they are increasingly vulnerable to cyber attacks. Traditional substations use classical encryption methods to protect data, but these encryption techniques are becoming more susceptible to sophisticated attacks as computing power increases. With the advent of quantum key distribution (QKD), quantum-based substations can offer unbreakable encryption. QKD ensures that any attempt to intercept or tamper with the encryption keys is immediately detected, making it virtually impossible for cybercriminals to breach the system without alerting operators. This level of security is particularly important as power grids become prime targets for cyber attacks, especially in critical national infrastructure. In terms of fault detection and response, traditional substations typically rely on manual intervention or semi-automated systems that are based on classical algorithms. These systems, while effective in many cases, often require human input to confirm and address faults. This process can be slow, especially in complex grid environments where multiple faults or disturbances may occur simultaneously. As a result, the time taken to isolate and resolve these issues can lead to longer outages and decreased grid stability. Quantum technology-based substations, however, can operate autonomously, detecting and responding to faults in real time with minimal human intervention. By leveraging quantum computing and 5G-enabled communication, these substations can quickly identify the exact location of a fault, isolate the affected area, and restore service to unaffected parts of the grid almost instantaneously. This level of responsiveness dramatically reduces downtime and improves overall grid resilience. Load balancing is another area where quantum-based substations excel. Traditional load balancing techniques often struggle to adapt to the rapid fluctuations in power generation and consumption, especially with the increasing integration of renewable energy sources like wind and solar, which are inherently variable. Traditional substations use centralized algorithms to manage load balancing, but these systems can be slow to respond to sudden changes in power generation or demand, leading to inefficiencies or even instability in the grid. Quantum-based substations, on the other hand, use real-time communication via 5G and advanced algorithms including quantum algorithms to dynamically adjust load balancing. This allows the grid to respond almost instantly to changes in power flow, ensuring that supply and demand remain in equilibrium even as renewable energy generation fluctuates throughout the day. The ability to optimize load balancing in real time is crucial for maintaining grid stability as the energy mix shifts toward more distributed and intermittent sources. In terms of automation, traditional substations typically use supervisory control and data acquisition SCADA systems to monitor and control operations. While SCADA provides some level of automation, it still requires significant human oversight for decision-making, particularly when dealing with complex events or faults. This reliance on human operators introduces delays and potential errors, which can compromise the efficiency and reliability of the substation. In contrast, quantum-based substations are designed to operate with minimal human intervention. By combining edge computing, 5G communication, and advanced automation algorithms, these substations can autonomously manage many of the tasks traditionally handled by operators. This includes real-time fault detection, grid control, and load balancing, all of which are executed with greater speed and accuracy than manual processes. The result is a more efficient and reliable substation that can adapt quickly to changing conditions without the need for constant human oversight. One of the most significant advantages of quantum technology-based substations is their scalability. Traditional substations are often built on legacy infrastructure, which can make it difficult and costly to scale operations or integrate new technologies. Upgrading traditional substations to handle modern communication and automation technologies requires significant investment in both hardware and software. Quantum-based substations, however, are inherently more scalable due to their reliance on 5G communication networks and quantum communication systems. These technologies allow for the seamless integration of additional substations, components, and devices without compromising performance or security. This scalability is particularly important as power grids grow in size and complexity, with more distributed generation sources, energy storage systems, and electric vehicles coming online. The ability to efficiently integrate renewable energy resources is a key differentiator between traditional and quantum-based substations. As the world moves toward cleaner, more sustainable energy sources, power grids must be able to accommodate the variability of renewable generation. Traditional substations, with their slower response times and less adaptive control systems, often struggle to manage the fluctuations in power generation from solar and wind energy. This can lead to inefficiencies, grid instability, or even curtailment of renewable energy production. Quantum-based substations, on the other hand, are designed to handle these challenges with ease. By leveraging real-time communication via 5G and advanced optimization algorithms, quantum substations can dynamically adjust to changes in power generation, ensuring that the grid remains balanced even as renewable energy production rises and falls throughout the day. This ability to efficiently integrate renewable energy is crucial for achieving sustainability goals and reducing reliance on fossil fuels. Quantum technology-based substations, with the integration of 5G and quantum computing, represent a significant leap forward in the way power grids are managed and operated. These advanced substations offer faster communication, enhanced security, greater efficiency, and better integration of renewable energy resources, making them essential for the future of modern power infrastructure. As energy demands increase and the shift to clean energy accelerates, the role of quantum technology-based substations will become increasingly critical in ensuring the reliability, security, and sustainability of the electrical grid.